Okay. So some logistics to start. Homework 2, I think it's due on Feb 2nd. I had an error on the website. We moved it on Feb 2nd. Reading responses for the paper presentations from the first session are due today. It's by end of day. If you presented, you don't have to write one, but if you want, you can write one. I don't mind. But yeah, those are the only logistics I can think of. Otherwise, please bother your TAs all week. Give them a hard time and get your homework done. It's usually fun when it works. Any other logistics that I'm missing that you all have concerns about? All right. Okay, so today, the way we're going to structure our class, we're going to recap a little bit on what feedback control is. We're going to study this paradigm called bang-bang control. And then we're going to do PID control, and then we're going to touch on a method called pure pursuit, or we'll see how far we get. But the idea is to instantiate a lot of the more abstract concepts we discussed last time in methods you might actually implement, right? And so let's start by just recapping what we had talked about. So we talked about this sense, plan, act paradigm, right? So in control, what we're going to do is we're going to assume that you know where the robot is. So you've done state estimation or Bayesian filtering to figure out where the robot is. You're going to assume that a planner is going to tell you like a rough sequence of waypoints or a trajectory that you want to follow. And control is going to follow those waypoints in the presence of stochasticity or no, right? And so the piece of the puzzle that we talked about is assuming you know where you are and you know where you want to go in the long term, how do you actually go there? How do you find the actions to go there in the presence of noise and the presence of complicated models of the world? Right? That's the problem of control we're going to think about. And specifically, we talked about feedback control, and we talked about how when you run open loop trajectories, you can have compounding error. You can drift from the path that you desired because the models are wrong, and you have unmodeled effects in the environment, right? And so you typically want to measure the error between your robot and your desired position and try to minimize that error. And so we talked about, how we can choose things like reference states on the trajectory that you want to get back to, computing error to the reference state. And then we discussed how we can instantiate the control problem as trying to take your current position, the error to where you want to go to, and trying to figure out what the actions to take on the system are, right? And so, for instance, for a race car, your action might be the steering angle or the velocity, and that's going to help you correct for these errors in closed, right? And so the steps of doing feedback control are first get a reference path or trajectory for planning. Then once you're executing things in real time, pick a reference state from the trajectory where you want to get back to, given where you are right now. Try to compute the difference between where you are, where you want to go to, and then compute what we call a control log given your current state and where you want to go. Okay? And so you start with one, and then you repeat 2, 3, 4 in a loop while you're still trying to accomplish your task. Make sense? Okay. So we talked about how we can instantiate this error in some frame of reference stuff, right? So we can get into the right frame of reference. But the important bit, what we're going to discuss today, is how do we compute control laws? So given your current state and your error to your desired state, how do you decide what control or what action to take? And the choice of action is up to you as the designer of your system. It can be a speed, it can be an acceleration, it can be whatever you would like. But in pretty much most of these cases, we're going to try and design what this function K is going to be. That's going to take in your state, take in your error, and give you control. So the discussion today is just going to be on designing the state. Yeah? Designing a rule for the state, which takes in a state, takes in an error, decides the control. That's it. And we're going to cover 3 different methods today. We'll cover a much more complicated method on Wednesday. But each of these methods have different trade-offs, so don't blindly follow one versus the other. Right? So specifically, we're going to cover these types of methods. Well, bang-bang control is silly, so I haven't included it on here. But PID control and pure pursuit is what we'll cover today. And then next class, we'll cover LQR, and the class after that, we'll cover MPC. But they're all just different ways to instantiate this general formula of taking your state and your error and producing a control. They're all just different cases, right? Okay, so Everyone on the same page for what we want to do with it? Yes? Great. Okay, so let's start by thinking about bang control. So let's say we're doing path following and you computed the error and the reference path like we talked about last time. What is the stupidest possible thing you can do? Just done. Like you're following a path, right? And you like drifted off the path. And let's say the control is just steering and you're just choosing a steering. What is the like silliest thing? Yeah. Steer backwards. So steer back towards the path, right? That's all that bang control is, right? It's just saying that you choose between hard left and hard right. So if you're to the left, then you go right, and if you're to the right, then you go left, right? But essentially, the reason it's called bang is because you like choose actions at the limits of your action range, right? So you say your control profile is going to be, if your error is high positive, your control law is going to be the maximum negative. And if your error is high negative, then your control law is going to be high positive, right? And so you just go bang between the two ends of your spectrum, right? And so the control law is just going to be like that. It's like the silliest possible K that you could have. Okay, so this seems dumb, right? So in what situations might this be good? Like when might you want to use this?
If you're going right at something.
Right, if you're going right at something, but even then you might have drift. So imagine you're going right at something, you drifted off, and now you're aligned.
If something comes in front of you that you're.
Right, yeah, that could be one. Another is if your system is like relatively like you're able to correct pretty fast in the loop, then it's going to be fine. But if you're going pretty slow, then you will like drift off too far and then come back and then come back, and then you have like a kind of winding thing. So when you're doing high frequency control, it's okay. But if you're doing low frequency control, that's kind of a problem. But if you're doing high frequency control and you're doing bang, what could happen to your system? Like physically, you have a physical system and you're doing bang control. Like, why might that not be a great idea? Yeah, you're constantly flipping your motors one way versus the other, and so that might damage your hardware, right? So generally, bang control is a bad idea, and so more formally, you can show that these bang controllers are not necessarily guaranteed to ever converge, right? Basically, you've gone too far, right? And then you like apply control and you go too far this way, and you apply control and you go too far this way. And so your system is like not stable, as in you never converge to zero. Your error never converges to zero, right? And so if it's okay to do that, it's okay to wind your way around the path, and it's fine. But in most systems, you don't want your helicopter doing like, you know, daisy chains around the path. Yeah.
If you're using this like in a car and you're making a hard turn to correct something,
Right.
Is there a chance that you could like kind of smooth it out a little bit?
Right, but hopefully that you have feedback so you can recover, but certainly there's systems where if you like take it too far, you can go unstable and like never recover. And so that's why you want to run feedback at a fast enough rate, and you want to pick a feedback law that guarantees convergence, guarantees stability, and bang doesn't. Right, so like, you're totally right that if I swerve too far, I could go in a path like down the pitch, I can't recover, right? Whereas if you have a feedback control loop that tries to guarantee convergence, then at least that will. Okay, so bang control is the silliest thing you could do. You all should implement it on the car. You'll see how silly it is. And then you'll do a better method, right? And so really what you want is that intuitively, if you've gone really far off, you want to like have more action bringing you back. And if you're like a little bit off, you want your action to be small, right? So you want really the magnitude of the control that you provide to be proportional to the error. Yes. This is nice because it's not a basic sanity check, which is saying if you don't have any drift, then you like are providing no action. As soon as you have drift, you start providing action proportional to the error. And so that's really the idea behind our next method, which is PID control. Right? So how many people have heard of PID control? Good. Yeah, around half. But let's go over it in some detail, and we'll see when it works and when it doesn't work and so on. And so I guess PID control was all introduced like quite a while ago. Not in the context of robotics, it was like introduced in the context of industrial, like chemical plant control and so on. When you want to keep your chemical process around a particular value, often you use things like PID control. If you want to do things with the humanoid, don't use PID control. It's going to break your humanoidization. And so then you want to use some of the more sophisticated methods we'll talk about next. But the idea of PID control is that you want to pick a control law that is stable, right? So it sends your error to zero, it keeps it there. And essentially the intuition is the same as what I said earlier, is you want to provide error, which is proportional to the, you want to provide control that is proportional to the amount of error, right? And so the form of a PID control law looks something like this, right? So it's like, let's say your error is error CT. We're only going to measure cross-track error. So only going to measure error from, we're not going to change velocity, just steering angle for the car. So it's going to be a combination of three different terms. One term, which is just a proportional factor on the error, so Kp times ECP. One term, which is proportional to the integral of the error, right? And one term, which is proportional to the derivative of the error. So the reason it's called a PID controller is because you have three different terms, right? You have the proportional term, which is representing the present. You have the integral term, which is representing the past, and you have the derivative term, which is representing the future. And so intuitively, you can think of the ECP is like, what is the error right now? Right? Integral ECP is what has the error been in the past historically, and E dot CP is measuring how's the error changing, so it's trying to predict the error in the future. Right? And so to do a full PID controller, often you want to combine this proportional term, this integral term, and this derivative. Okay.
Any point of the derivative negative?
Yep. Yep, the derivative could be negative, yeah. Like, all of these can be negative. So they're not like sign restricted because you might want to go one way versus the other. So the derivatives can be negative. But it's usually some combination of these, right? And these terms we have here, the KB, KI, and KP, are what you'd call gains, right? And these gains basically determine how much do we care about the current error versus the integral versus the derivatives. And often they're chosen differently for different systems and for what problems you want to solve. And so we'll talk about how to tune them, but the intuitive idea is you want a control law that combines the error, the integral of the error, the derivative, yeah, linearly. Okay. So you can kind of think of this as intuitively implementing three pieces of intuition. The first is the proportional controller, which is saying, all you want to do is take an action to minimize the current error, right? So it's like, imagine that your ECP was high, your action is going to be high, right? It's like proportional. And your gains are going to be positive. And so it's going to say, okay, if you like drifted a lot to the left, you're going to take a large action. So it's saying, make your action proportional to your error. What your integral term is going to say, this is like not immediately intuitive, we'll cover it in a second, but your integral term is saying, if you're accumulating error, right? So which means that your integral keeps increasing. So if your error had gone to zero, your integral stops increasing. But imagine your error was still accumulating, right? Then your integral keeps growing. And if your integral keeps growing and you're continuing to accumulate error, then it's saying try harder. And so it's like, imagine you had like almost solved your problem, you've gotten pretty close, but you weren't like finishing the last bit. What the integral term is going to say is that like the integral keeps building up. And so it's going to say you're not quite getting there, try harder. And the derivative term is saying you're going too fast, right? So your system's going to oscillate too much. You're going too fast, so let's slow down. So essentially, you can think of this as applying the brakes. This is like applying the acceleration towards zero or zero error. And the integral is like giving you the last bit of juice to like reduce that thing to zero. Right? So intuitively, those are the three terms and why they matter, and we'll cover each of them. How do we feel about the situation? It makes sense? Question? Yeah. Oh, like 0 to t. So it's like 0 to the current time step, because you can't compute the integral in the future. So it's going to be, what is the sum of errors of everything you've seen in the past? And so it's like, okay, imagine that you had come pretty close to 0, but you were still like, there was like something like a constant offset, which is not letting you go down to 0. And if you have this constant offset, which is not letting you go down to zero, the integral term will keep growing. Right? If the integral terms will keep growing because your ECP is non-zero, right? And so as you go further and further and further, your ECP is going to be non-zero. And it's going to keep growing, which means the integral term will keep growing. And so what the integral term ensures is that your steady state error goes to zero. So like your system converges to zero error. Right? And I'll cover them in detail. So I think it'll become more clear with the example. So let's start by thinking about proportional control, right? So proportional control is just saying apply an action which is equal to like negative KP times EC, right? So it's saying that if you're to the left of steady state, right, then you apply an action which is proportional to how much to the left you are, scaled by some linear constant. And so it's just saying apply something proportional to send you back to zero, right? So it's always pointing in the opposite direction of error, but it's scaled by some linear proportion. So this is like the easiest thing you can think of, right? So it's saying, let's say you started here with some ECP, you're going to apply an error, you're going to apply an action which is kind of sending you back towards steady state, right? And so you're going to now have, you're going to move your car some amount, right? So you moved your car some amount towards the steady state, and now your ECP is going to be smaller, right? So your action is going to be smaller. And so typically what you'll have is that you'll have actions that look like that, right? So it's like you'll apply a large amount. You'll have something that is large at the start, and then as you keep getting closer and closer to zero, the amount of control you're going to apply gets smaller, right? So if you keep running this through, right, you will say here, okay, the control is, the error is smaller, which means the control is still happening towards the middle, but it's less strong, right? Less magnitude. And now, because you're not like at a system that can magically teleport, you might overshoot the zero steady state, right? If you overshot the zero steady state, now the error has become positive, right? Which means the action becomes negative. And so when I say error, I don't mean absolute error. You have to take like directional error. So just take like difference between where you are and where you want to be. And so your error is now positive, which means the action is negative. So it's going to send you back towards the middle, right? And now you're going to be sent back towards the middle, and then that's going to repeat until you hopefully converge. Yes? It's different because you're scaling the amount of action that you are taking according to the magnitude of the error. Whereas in Bang Bang, if your error was negative, you max out, and your error is positive, you max out the other way. And so it's important because like this thing will reduce the amount of control that you have when you're close. Whereas in Bang Bang, if you're here, you still apply the maximum possible action. And so that won't converge. Okay, so let's try and like understand what happens with this controller a little more carefully, right? So what happens when the gain is pretty low? So what happens when KP is like pretty small, right? So we have this control law KP, and let's try to think about what happens when KP is set to be pretty small. So what's it going to do if KP is pretty small?
That should be a small action.
It's going to take a small action, which means that it's going to try and converge to the steady state pretty slowly, right? So it's going to try and go pretty slowly towards the steady state. And so the controller is going to be pretty loose, and you're not really going to track the positions you want to track, right? Because you're going slowly. And what happens when the gain is pretty high? Yeah. You have oscillating behavior, right? So you have like behavior that like starts to oscillate like that. So the reason it's oscillating is because your controller is like snapping pretty fast, right? So if you're snapping pretty fast, you'll see that it like snaps, it like applies so much force that it like overshoots the zero, and then it applies force again, it overshoots the zero again, and so it like oscillates rather than converge, right? And so you often want to tune in your P term, you want to tune it so that it's not overly slow in getting to the steady state, but it's not oscillating. And so you want to keep it somewhere in between. And oftentimes there's like a tuning procedure that we'll study that helps you set this parameter. If you want to like derive this mathematically, try taking a linear system, right? Try plugging in the control law, which is equal to this thing, right? So like have, you know, x dot equal to ax plus bu, right? Plug in u as minus k times the error, right? Error is like x minus x reference, and like do some integrals, and you will see that it's like an exponential curve, right? And the exponential curve is like oscillation. The period of oscillation is going to depend on the choice of k. And so if you want to like, I'm not going to go over this in class in detail, but if you want to do this mathematically and kind of understand it, try studying it in a linear system context, right? So like write out a linear system, substitute this law into your linear system, write out the integral. It's like an easy integral. And then you can derive what the like x is going to evolve as. And you'll see the x evolves kind of like an exponential function. And depending on the choice of k, that exponential function has different properties. Right? Okay. Does that kind of like make sense? But I think it's not really that important to like get that detail right as much as it is the intuition, which is if the gain is low, you go super slow. And if the gain is high, you start oscillating. And so you want to stay somewhere in between. Yes. Okay. So that is the p term, right? And so if the gain is really high, you start having this like chase your tail type behavior. So you like will overshoot and you overshoot and you overshoot and you overshoot. So if you ever are like, you know, playing with the race car, try increasing the gain a lot. You'll see that it basically behaves kind of like band back control. And usually this makes sense, but if your KP is too big, it's almost like you max out your control no matter what. Right? And so it passes a sanity check. Yeah.
Is there, even if the gain is really high, is it still guaranteed to converge eventually? It just will take a really long time.
Not for all cases, I believe. Yeah. Okay, so we've said that we've talked about proportional control. Proportional control is great when you have like a system that is just drifting off because of some noise. But imagine that you're in a situation where there's like wind blowing against your car, right? And it's like a constant wind that's blowing against your car, and basically the wind is like not under the control of your system, right? And so you're gonna like basically if you have a system where there's wind and you keep applying just the P controller, at some point the wind and the controller are just gonna balance, right? You like, and you'll see that the system doesn't actually converge to zero. Right. So if the wind is not under your control, at some point there's like a steady state offset. The wind and the controller will balance and you'll kind of end up like somewhere here. And the controller is like not going to go to zero. And that's when you want the integral control. So to Leo's question earlier, basically what the integral control is going to say, right, is that if you have some amount of accumulating error, like imagine that your wind and your error balanced out and you were like not at zero, but you were like kind of close to zero, but you really want to set that steady state error to zero. You like wanted to converge right to the point you want. What's going to happen if you have an integral term, right? This is going to be the integral from 0 to t, your current time step. Is that if your error is not zero, if this term only stops growing if your error is 0, right? Because otherwise there's still a positive thing or there's still like something that is being right? And so the point is that if your error is not 0, this term will keep growing. And so it's like, okay, your steady state error is not 0. I'm going to keep increasing how much action I apply to this term till I like send it back to 0. Because that's the only place this will stop growing. Right? So it's saying like, if the wind and proportional control balance each other out, then the integral is going to keep growing until you send the steady state to 0. And when the steady state is 0, this integral no longer keeps growing. Right? Like imagine you reach 0, ECP is now 0, so the integral stays fixed. Right? And so the important thing to think about is proportional control sends you back to the steady state. But in the presence of like constant disturbances or offsets, right? The integral term kind of like will try harder to overcome things that the proportional term cannot. Does that make sense?
Yeah, but then like that, even though this integral is not growing, isn't like the integral still like contributing to a certain direction?
Yeah, but you can think of it as like integral is contributing to going in a certain direction, but the wind keeps going in the other direction, right? And so like proportional plus so at convergence, this term is going to go to 0, right? Because ECP will be 0. And this term will not be 0, but this term is just gonna counter the wind. Right? So the problem is that if you just use a proportional controller, like you will never have the offset to counter the wind, right? Because as soon as you hit, like ECP is 0, like this thing will stop applying force and then the wind will take over, right? And so the point is that it balances somewhere that's non-zero, and the integral term will like make up for that extra disturbance. Right? So you can think of the integral term as essentially overcoming like trying to set the steady state error to 0. When I say steady state, I mean at convergence, you want this thing to get to 0. Does that make sense? And so the integral here is going to be from 0 to t. So it's like, imagine that you like, you think of an integral like a sum. It's just a sum, right? So if you like discretize your time, it's just like a sum of the errors across them. Yes. So all you're saying is that like, you don't want to keep accumulating. You want your system to. And if you're like interested in things beyond this particular lecture, you should look up this field of like adaptive control. Integral control is the simplest version of adaptive control.
So KI then would be basically the scalar for that proportion. That's it.
And so you scale the integral term by some Ki, and that Ki lets you like compensate for that steady state. Right. And so essentially this is going to keep sending you back towards the, it's like not going to let you get stuck somewhere. It's going to like keep sending you back towards the steady state. Right. So that's why you need the I term, because oftentimes you'll have like gravity or like wind blowing or like other external factors that you want to compensate for. You don't want it to get stuck somewhere. Yeah. So what have we done so far? We've introduced a proportional term, which is saying go back in the opposite direction of error. We've talked about an integral term, which is saying don't allow your system to keep accumulating error. So you're sending it back till it no longer keeps accumulating error. Right. And so the point here is that if you have some steady state offset, the steady state error, the integral term is just going to squash it. Okay? Because it like will not accept growing error because it's going to keep increasing the magnitude until that error goes down. Okay. Do we buy this? So that is PI control, right? And P is derivative control. And you can think of this intuitively as saying, if you're, so what it's doing is it's like, it's penalizing the derivative, right? So it's saying that like, if your E dot CP is super high, then like penalize control. And what that means is that if you're changing too fast, like if you're swerving too hard, like slow it, right? It's just saying apply the brakes. So the derivative term is just saying if your gradient is too high, right? So if it's saying, like imagine that you were here, your KP term was really high. So you're applying like a huge action. So you're, which means that your derivative E dot is going to be pretty large. All that this KD term is going to say is going to like slow you down, going to apply the brakes. Right. And so when we talked about the proportional controller just like oscillating and so on, right? You can think of this derivative term like a damping term. You have a spring, right? It's like a damping term. So you can almost think of the proportional controller like a spring and the derivative controller like a damper. If you have a spring damper, it's like literally it's the same equation. And so it's literally a damper on the spring. So what it's going to do is it's going to ensure that you like don't keep oscillating, but you like slow down and you don't change too fast and you convert to the steady state. Right? Because oscillations are never good for a system. Yeah.
This doesn't take care of wind then.
No. So that's why you need the I control. Right? Because in some sense, like imagine that you had like read something with the ECP was not changing, like this thing is not gonna, it's not changing, but it's not zero. This thing is not.
So error doesn't accumulate where you're at, it's based off of your
Right.
action.
Exactly. Yeah. Because it's the derivative of the so okay, so this is like so we talked about the integral controller and we said, okay, hey, the integral controller we can implement by like discretizing time and summing up things over discretized time. But how do you implement your derivative controller? You have to get this. The law is basically, you know how to get error, right? Because we talked about how to take the difference between where you are, where you want to be. Let me give you this, right? This is subtraction. How do you compute E dot? Like what is E dot, right? And I made up this term. Like how do you compute the error dot?
You can just like look at the previous points, like average or change, or you can go back and like 2 points for like get even more accurate results.
Exactly, exactly. So you can use numerical differentiation or finite differences, right? So you can say, look at the current value of error, look at the previous value of error, and take the differences between them and like divide it by the time step. And that's going to give you the grade, right? Now you obviously want the time step to be small enough that it's accurate, but that can give you an approximation to E dot, right? So that's one way of doing it, right? But that's what again the thing about numerically differentiating the error. Now, why is this a bad idea?
Put your error, not a lot.
You have noisy input, you accumulate error. So instead, in this particular system, right, you can like actually compute the analytical derivative, right? So for instance, you have ECD, right? It's the difference between X and X ref and Y and Y ref projected into the right frame of reference, right? The same thing we did last class, right? You can just take the derivative of this thing with respect to time, right? And you can write it out in closed forms. So in this particular example, it's not true everywhere, not true for every system. But in this particular example, you can compute the derivative of the error with respect to time. And like this thing doesn't have numerical issues because it's like a closed form thing. Right? If you know the difference between where you are and where you want to be, and you know the velocity, right? Then you like know what the change in error might be. And so you can compute that E dot term that way without having to do it numerically. But if you like didn't know the system equations this way, you didn't know how to take derivatives to them, you can always do it numerically. But that's more prone to this. And so if you can use system structure, you always should. If you don't have the system, then obviously you just do it numerically. Does that make sense? Okay. So the problem with derivatives is that if you have a noisy system, right? Imagine your system is like moving around a bit, the derivatives are changing all the time, right? And the derivatives are like non-zero, they're like high. So any noise in your system can lead to huge control variations, right? So it's like, if you look at this plot, for instance, right? You can see here that there's just noise in the system, but you can see that it changes the like slope a lot. And if it's changing the slope a lot, that's going to lead to a huge D-term, right? So in lots of practical settings, you don't actually use the D term as much, you just stick to the PI terms because often the D terms amplify noise. Right? Basically anything where your system is like going back and forth, where your derivative of your error is changing a lot, like that's going to like increase the magnitude of actions a lot. So if this was the controller, this is the actions, you can see that when there's noise in the system, the actions kind of blow up. And you don't always want that. So while it can help with oscillation, often what people do is they just control the magnitude of P, they don't make it so large, rather than using D, because D like goes up with noise in their system. We follow that? So kind of like putting the pieces back together, right? We have this PID controller, which is a combination of the proportional term, it's the difference between the current and the reference, the integral term, which is a sum over all the past errors, and the derivative term, which is kind of trying to predict the future by seeing what the rate of change of the errors, right? And so the proportional term is trying to bring you back to the middle, integral is dealing with steady state, and the derivative term is trying to slow down or put the brakes on your system so you don't oscillate. Okay, so that's the PID controller, super simple. Do we buy that? Will we implement it tomorrow? Great. So homework 3 will be due on Friday. But yeah, so the nice thing about the PID controller is that it's like very much system agnostic, right? Like nowhere here have I used the system. I like define this motion model, I define this car model and sensor model and all this fancy stuff. And then I like use this dumb as hell law to do everything, right? There's no, it's just proportionalities on error. Maybe the only place I use the model was to compute the derivatives, but you can even do that numerically, right? So nowhere in this whole system did I use the model at all. So that's why like people love to use PID because it's so easy. And so easy and so system agnostic that you can use it anywhere. And it works surprisingly well. So, and one thing we've like, alluded to, but haven't really described is what are KP, KI, and KB, right? So we've talked about the effect of KP and we've talked about the effect of KI and the effect of KB, right? But like, how do you fix them? If I write a KID controller, how do I fix them? Any ideas?
Start with one and then two next line.
Start with one and two different. That's pretty much what we do. But the tricky part that you might have then is that there's like interactions between the terms and you might not get the global optimum. But often methods for like doing this empirically do something of that nature, right? So one of the methods that is popular is called GAN method, right? And so this is kind of the flow chart of what they do, but intuitively you can think of it this way. Like set the Ki and Kd terms to 0, right? And then just try to increase the Kp terms slowly. And so try to increase the proportionality terms slowly. So we said when it's slow, it's gonna like go slowly through convergence, and when it's too high, it's gonna oscillate a lot and potentially become unstable. So what you wanted to do is increase it slowly until you get to a steady state oscillation. So the oscillation that repeats and doesn't grow in magnitude. So you want to get the steady state oscillation. And when you get the steady state oscillation, you can measure the like period of oscillation, right? And what K you had to get there. And then you can apply they like try to run a bunch of systems and they have these rules to pick KP, KI, and KD from like the period of oscillation and what the value of K was. And so they're saying, okay, you first use P, like you use the P controller to almost like probe the system to figure out how it oscillates, how it accumulates that. And then according to that, you can pick the Ki and Kd. Right? So there is like literally a table, you run it till you get the steady state, then given that you just plug in the numbers into your table and you get your Ki and Kd. And so this is like a very empirical method. I don't know if there's any theoretical justification for it. But it like seems to work pretty well. Okay? But if you all invent a better method, we should publish a paper. That'd be good. Okay, but that's the general idea of PD control, right? Or PID control. We've gone from our problem of feedback control. We've said, okay, band control just like applies maximum control opposite of the direction of error. And PID control tries to do it in a proportional way, while also accounting for accumulating error and for overall oscillation, right? So P, I, and D is trying to get you back proportional to the control. I is accumulating error, and D is trying to not make it oscillate. So that's PID control. Any questions? No? Feel pretty good about it? Great. So the next thing we're going to think about is this idea called pure pursuit, right? And pure pursuit is like intuitively you can think of it as like you're just like chasing a carrot, right? So your car is like chasing a carrot further along the path always, and you're gonna try and like compute a control law, which is always chasing a carrot. So imagine if you had two fighter planes like chasing each other. It's like you're always trying to compute the arc, which lets you keep chasing the other carrot. And so the idea of pure pursuit is just like trying to use the model of the system in order to compute how to keep chasing the carrot. And so let's look at this a little more closely, right? So we've defined this model for our car, right? And we've like written out all these equations, but our PID controller didn't use the model at all, right? So it didn't use all the structure you have in your system. And so what pure pursuit tries to do is rather than just try to compensate for error, which is very negative, what pure pursuit tries to do is it tries to look ahead planning of it. So it tries to say, given this model of the system and where I want to go in the future, can I compute actions that take me to somewhere else in the future using the model of the system, right? So the difference between PID and pure pursuit is that PID doesn't use the model of the system anywhere. And pure pursuit tries to use the model of the system to like chase this carrot. And so it'll become more clear when I show you a picture. But that's like the basic difference between PID and pure pursuit. You're trying to like use the system where you can. And so the key idea that we're going to use in pure pursuit is that the car is always moving in a circular arc. Right, so we talked about, if you remember our classroom motion model, we said the car is always moving in a circular arc. There's this instantaneous center of rotation. You're always computing the arcs that it's moving in, right? And so, especially if you think about your race car, you're like doing this Ackerman steering, so you're like always going in an arc. And so it's just going to use that fact to figure out what controls to take so that the arc gets to where you want it to get to, right? And so if you look at it this way, right? Let's say we go back to our feedback control problem. We have done look ahead, so we've chosen a point somewhere in the future. What we want to do is figure out a control law, which is going to get the car to like go there, right? So imagine that we, the car is right here. You wanted to get here. That's the reference point we chose, right? And so if you did PID control, you would just do like direct differences. You're not using the fact that the car moves in the arc. You're not using anything in the control of the system. It's just reactive. But in pure pursuit, we're going to use the fact that the car moves in these circular arcs to compute what the action should be so that this arc from this car position will intersect with the point you want it to get to, right? So the difference is just one is very reactive without model of the system. Pure pursuit uses the model of the system. That's it. Make sense? Okay, so let's consider this setting over here. Your car is at some position X, Y, and some heading. You want it to get to some position in the future, X ref and Y ref, such that the difference between X and Y is L. Right, so some point on your reference trajectory in the future. And what we want to solve for, since we're only controlling the steering, is what steering angle will make sure that the arc of the car gets it to that point. X ref, Y ref. Yes? Okay. So we always want to solve for an arc that passes to a look ahead point. And the important thing here is that this point is not stationary, right? The point keeps moving. So if you like consider how this is going to be, that you're going to like start here, you're going to choose a reference point, right? You're going to compute a point along the arc. Now you move somewhere else. You'll probably choose a reference point here to compute a point on the arc. And so you're going to keep trying to like, as you keep moving, the reference point you want to get to is going to keep moving further and further ahead. And so you're going to like essentially keep running this process of finding the steering angle that gets you back to your reference point. You're just going to keep running it in a loop, right? So at any point of time, you want to compute the steering angle, take a step, reselect a reference point, recompute the steering angle, take a step, repeat, right? And so the process is just going to be find, look ahead, compute an arc, take an action in the world, right? The world transitions to a new point, repeat, find a new look ahead point, recompute the arc that gets you there, take an action, and keep going. And the reason to do that is so that we don't have this like behavior of getting here, getting here, getting here. So you just like smoothly keep going along your